Okay, welcome back. We're going to discuss now what we call non-elementary integrals. You may remember from, it might have been in Calc2, where we introduced integration and the idea of an antiderivative. And the idea is that we dealt with what was called elementary functions. Okay, so an elementary function is any function that is put together. It's an expression, it's a function that involves a combination of powers, trigonometric functions, or compositions of functions. So it involves the operations, right? So it's a finite number of operations. It's an expression involving a finite number of operations involving adding, subtraction, multiplication, division, trig functions, powers, those things, okay? Or a composition of those types of things, okay? So anything that's represented by that is what we call an elementary function. Now, an elementary function, just so you guys know, a non-elementary function doesn't mean that it's a simple function. Okay, so you can have some complicated looking functions that are still elementary. Okay, what we mean by elementary function is exactly what I just said. The definition of an elementary function is an expression, right? It's a function that involves a finite number of operations, meaning that you're using some combination of the four basic operations plus powers, trig functions, composition of functions. Okay, that's what we mean by elementary. Now, there are some integrals. Oh, well, let me take this. If you have an elementary function, right, as an antiderivative, so you have a function whose antiderivative is an elementary function, then you can use all of the basic techniques that we've been showing in this class to find that antiderivative. Okay, if you give it an integral. But if the antiderivative of the integrand is not an elementary function, then we can't use those techniques. And this is the other aspect, or the other situation, where power series comes into play. And a great example of where this happens is in probability theory. Okay, so if you've ever taken a class in statistics, or actually no, in this class, in a previous chapter, we talked about finding the probability distribution. Well, there are certain probability distributions you cannot integrate. Okay, for example, one of those is the normal distribution. There is no probability formula for finding the probability of a normal distribution, because the antiderivative of the function of a normal curve is not elementary, which we'll talk about. Okay, so let's use an example of how we do that. In fact, here's what we can say in general. So in probability, we know any function that has something like this, right? So any function that is of the form e to the x squared does not have an antiderivative that is elementary. So we can't just integrate this. So if we want to integrate this function, there is no closed form. Well, we say a closed form, okay? There's no closed form for this integrand, okay, or for this integral, okay? It doesn't exist. Well, it doesn't exist the closed form doesn't exist, okay? So one of the ways that we would have to deal with this, as far as, in fact, the normal distribution, is in order to find this value. For example, what if we wanted to find a probability of a range of values, which means we're looking for the area under the probability distribution. we would have to use numerical approximations, which we've discussed before, in order to estimate the probability. But we can also use power series to do that. Okay? So that's where we're going to do. Okay, so let's use this as our example. So let's say we have this example. And we want to express this integral right, as an infinite series. So the Maclaurin series for this, so we know the Maclaurin series for this is what? Well, we know e to the x, right? So we know e to the x is given by what? It's going to be x to the n over n factorial for n equals 0 to infinity. So that means the expression for this is going to be very similar to that. And all we're going to do is substitute in x. So that means e to the negative x squared is going to be represented by the Maclaurin series, n equals 0 to infinity of what? Negative x squared to the nth power over n factorial. And so now, what does this thing look like? Well, we don't have to expand it out. Okay, I know I've been expanding out the textbook, some expands it out, but look what we can do. So we can just rearrange this, right? So let's use properties of exponents. So this is going to give us what? It's going to give us n equals 0 to infinity. We're going to take the negative 1 out, so it's going to be negative 1 to the nth power, right? So we're distributing the n. Okay, this is x squared, so this is going to become x to the 2n power over n factorial, okay? Okay, or in fact, you can just pull it out here and just write this as x to the 2n over n factorial like that. Okay, so now that means, guess what? That means this is equal to the integral of what? The summation of n equals 0 to infinity of negative 1 to the n x to the 2n over n factorial dx, right? Which is what? Well, this is just, let's just introduce the term. So this means that we're going to take the integral of what? Well, this just gives us, well, at 0, this is just going to be 1. And then minus x squared over 2 factorial. Oh, no, I'm sorry. So it's just going to be x squared minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial, and so on, dx. Okay, so all we're doing is integrating this term by term, right? Well, let's do it. So if we integrate it term by term, what do we get? Well, that's going to give us c plus x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial, right? And minus, where are we at? Okay, there. And minus x to the 7th over 7 factorial, oops, not 7 factorial, 7 times 3 factorial plus x to the 9th over 9 times 4 factorial minus x to the 11th over 11 times 5 factorial plus, and so on. Okay, so that's what we get. And so what we end up with is this keeps going on and on and on. And our nth term is going to be negative 1 to the n. Okay, and then we're going to end with what? We're going to end up with x to the 2n plus 1, right? Right, because it was x to the 2n. So now it's going to be x to the 2n plus 1. And then down here we're going to get 2n plus 1 times n factorial. Oops. And it continues on and on and on. So now, that's the result. So now here's the thing that we want to do. Okay, so that's the first part. Okay, so now we found the series representation. Okay, so what we're going to do now is find the definite integral. Okay, so now what we want to do is, let's say, now that we've got the power series representation here, the Maclaurin series representation here, let's find this. So we want to go from 0 to 1 of e to the negative x squared dx, and we want to be within an error of 0.01. Or hold on, let me double check. Is it 0.01? Yeah, 0.01. So we don't want an error any more than, or we want it to be less than 0.01. So, first of all, we know that this is going to be equal to let me see here. Oh, so we're going to evaluate this at 1 and 0. Well, the cool thing is for a definite integral, we're not going to have the c. The c goes away. And so when evaluated 0, this whole thing goes to 0. So the only thing we have to really evaluate this is at 1. Okay? So that means that we can just plug in 1 for x, and this reduces to 1 minus 1/3 plus 1/10 minus 1/42 plus 1 over, this is going to be 24, is that right? Yeah, 24 times 9. And that's going to be 1/216. And so on. Okay? Now, the sum of the first 4 terms, right? So the sum of the first 4 terms is approximately 0.74. If you use your calculator, so if you add 1, 2, 3, 4, these 4 terms, so these 4 terms are going to be approximately 0.74. Okay, now, by the alternating series test, this estimate, because this is an alternating series, by the alternating series test, this estimate is accurate to within an error of less than the next term, right? And so the next term is 1/216. And 1/216, right? So 1/216 is less than 0.01. And so, this is our estimate, 0.74, and it is within 0.01. And we're done. Have a great day.